So this is one of the important questions, which is similar to parts that you can see in the exams. So we have a 240 DC shunt motor, and the motor has a constant field. And this is something you need to highlight, that the field is constant. So we need to write down that I field equal constant. And this is very important. Okay, and you need to repeat the same question if I field was not constant. Okay, so you need to think about repeating this question again with I field not constant. Now here we have our armature is 0.1, so we will sketch the circuit. So here is our source, the field resistance RA, and here we have EA, torque, omega, RA, RF, and the current here going into IF is constant, and here is IA, V source. Now let's continue. The machine is driving a fan load whose torque is proportional to speed square. Now if we go here, so the machine here has a mechanical coupling, so this machine is coupled here with a fan. Okay, so the machine will have a torque output T coming from the machine, which will drive this into this with a speed omega in this direction, and the load itself, which is the fan, will have a reaction here T of the fan. And if we are at a steady state, the torque coming from the motor will be equal to the torque needed by the fan, and at this stage your speed will be constant, and we call this the operating point, or we call this a steady state, and we will learn this in the torque speed characteristic. So at steady state the motor speed will be constant, and the motor will be running at constant speed. And for the motor to run at constant speed, the difference between the torque coming from the motor and the torque coming from the load should be zero. There is no acting torque, or there is no driving force, so we don't have an acceleration. Now if we look at this curve here, which I got from the internet, it's the torque speed characteristic for centrifugal pumps. And as you can see here, we have the torque, and here we have the speed, and this curve can be approximated like this. So we can see this curve is that the torque of the pump is proportional to the speed squared of the pump. And this curve is the same for blowers, and it is the same for fans, and it is the same for pumps. It's the same characteristic. So if you have a motor, and this motor is coupled with fan, or you have a motor and this motor is coupled with a blower, and or you have a motor and this motor is coupled with a centrifugal pump, so the torque of the load itself, T load here, T of the fan will be proportional to N squared. T of the blower will be proportional to N squared. T of the pump will be proportional to N squared. And don't forget that the machine itself will output a torque, and the structure will run in the same direction of the motor torque because it's a motor. And between this torque and this speed of the motor, there is a relation that we need to find, which we will find in the next lecture. So we know that the torque speed for loads, for this type of loads, is torque proportional to N squared. So this is for fans, for blowers, for centrifugal pumps. But what is the relation between the torque and the speed for motors, and this is a abbreviation I use for function. So the torque is a function of speed. What is this function is? This is what we will do next lecture. So let's go back to our problem here. So here we know that the torque is proportional to n squared, but which torque? This is the torque of the load. And let's see if there is anything here mentioned about mechanical losses. And as I can see here, there is nothing mentioned about the mechanical losses. So the mechanical losses are neglected because they are not mentioned. And this will make our life easy when we are solving this question. So the mechanical losses are neglected, and if we are neglecting the mechanical losses, this means that T developed equal to T output equals to T load at a steady state. So T out equal T load, so we don't have any acceleration because T coming from the motor minus T coming from the load equal to the inertia multiplied by the acceleration. So if we are running with constant speed, this means that the acceleration is zero, and if the acceleration is zero, T motor and T load will be equal. And if we are neglecting the mechanical losses, in this case T developed and T output are the same, because we are neglecting mechanical losses. Why this assumption is very important? Because we will now say the following. Now we can say that T developed is actually proportional to n squared. So we used the same equation for the load for our motor. So we can say that T developed is proportional to n squared. And this relation will be the key to solve this problem. Now let's continue reading the question. So we have the motor is connected to a fan load which has a torque that is proportional to n squared. Now we understand what is the meaning of a motor connected to a load with speed or with torque proportional to a speed squared. Now when the motor is running at 750 RPM and rated voltage, so rated voltage means this voltage up here, it takes 30 amperes. Find the required armature voltage to reduce the speed to 600 RPM. And as you are asked here to find the armature voltage, this means that your source is not constant. You are asked to calculate what is the source of voltage. But someone will say, okay, look, if I change its V source here, the current inside the field will change. No, in this particular question, it is mentioned that the field current is constant. How you will do this? We will learn this when we study speed control, which is the next lecture. So here I field is constant. This means he will change only the voltage here. How he is going to do this, we will learn in our next lecture. So we need to find this V armature so we can change the speed from 750 RPM to 600 RPM. And this is a typical speed control question. Now let's write down what we have here. So what we have here, so the machine was running at 750 RPM. And when the machine was running at 750 RPM, it was taking I armature of 30 ampere. I know in this question it's a little bit confusing because it is not mentioned that the current taken is armature current, but because there is no field here, the field is constant, so this current is armature current. However, in the exam I will mention clearly that the current is armature current. So here we can add that it takes armature current, so we can avoid any confusion. So the machine runs at 750 RPM, takes 30 amperes, and in this case V source equal V armature equal 240 volt. This is what is given. What we need to get, we need to run this machine at 600 RPM. So we need to do speed control. We need to change the machine speed from 750 RPM to 600 RPM. How we are going to do this? By changing V armature. What is V armature? So we can name this as V armature 2, and this is as N2. So here we have N1, here we have I armature 1, and this is V armature 2. And the question is, calculate this V armature 2. So how you deal with this DC machine problems? So as we mentioned earlier, the advice is try to start by one case, make this case as a full case, define every single variable you can do for this case, then go to the unknown case and use the ratios. Okay, now let's do it step by step. So let's start by case 1. So what we know for case 1, we know N1 at 750 RPM, and we know that V armature 1 is 240 volt, and I armature 1 is 30 amperes. And we don't need I field because I field is constant, so there is no idea to calculate I field. But we need to calculate E armature 1. So E armature 1 is 240 minus R armature, and R armature is 0.1 multiplied by our I armature 1. So this equal to 240 minus 0.1 multiplied by 30 amperes, which equal to 237 volt. So in this case, which is case 1, we know N1, we know V armature 1, I armature 1, IF1 is constant, EA1. Also, if we need, we can calculate T developed, but there is no need to calculate T developed. Now let's go to case 2. In case 2, we know that E armature 2 equal to V armature 2 minus 0.1 I armature 2. This is one equation. And as you can see in this equation, we have three unknowns: E armature 2, V armature 2, I armature 2. So we have one equation in three unknowns. So how we can deal with it? So we have one equation in three unknowns. So we need two other equations. So we need another two equations. So how we will get these two equations? So the key here is to use the ratio EA1 divided by EA2 equals to IF1 divided by IF2, N1 divided by N2. And it was given that the ratio between I field 1 to I field 2 is 1 because the field is constant. So E armature 1, we have E armature 1 as 237. E armature 2 is unknown. First speed is 750 RPM. Second speed is 600 RPM. So from this equation, we can get E armature 2. So E armature 2 equals to 189.6 volt. So now we have E armature 2. So to get V armature 2, we need I armature 2. So the question is how we can get I armature 2. So how we are going to get I armature 2? So to get I armature 2, we mentioned if you need to calculate current, think about torque. And if we need to calculate torque, think about current. So to calculate I armature 2, we need to write down an equation for torque. So how we are going to write down an equation for the torque? So we know that T developed equal to K motor IF IA. So if we write the equation for T developed case 1, which will be K motor IF1 IA1, and if we write the equation T developed 2, which equal to K motor IF2 IA2, and if we divided the two equations, we will get rid of K motor. So we can say that T developed 1 divided by T developed 2 equal to IF1 divided by IF2 multiplied by IA1 divided by IA2. Also, we have IF1 over IF2 equal 1 because the field is given as constant. Now we will have this equation, t developed 1 divided by t developed 2 equals to I armature 1 divided by I armature 2. So I armature 1 is 30 amperes, I armature 2 is unknown. Now we have an equation which has I armature 2, but we still here have T developed 1 divided by T developed 2, which is unknown. I know we can go back and calculate T developed 1, but what is about T developed 2? So what is the idea here? How we can get a relation between T developed 1 and T developed 2? This is what we said at the beginning is the key of the question. So the key of the question is that T developed is proportional to N squared because you have a fan load. So because we have a fan load, this torque will be proportional to the speed. So if we go back and apply this rule, so we can say T developed 1 divided by T developed 2 equals N1 divided by N2 all squared. This is because T developed is proportional to N squared. So given this, we can write that 30 divided by IA2 equals to N1 divided by N2 squared equal to 750 divided by 600 all squared. So from this equation, we can get I armature 2 as 19.2 ampere. So once we have I armature 2, we can go back to this equation. So in this equation, we found E armature 2 to be 189.6, and we found I armature 2 to be 19.2. So the only unknown in this equation will be V armature 2. So we can say that V armature 2 equals to E armature 2 plus 0.1 I armature 2. Equals to E armature 2 is 189.6 plus 0.1 multiplied by 19.2. This equals to 191.52 volt. So this is V armature 2. Now to summarize this, let's add one page here. So we had a DC motor, we had a field, we have the armature here, and this motor has EA, and this motor is coupled to a fan. This fan was running at 700 RPM, and we needed to take the speed down to 600 RPM, and this is called a speed control. So how we did this speed control? So we did this speed control by changing this voltage V armature. How we will do this change, we will learn this in our speed control lecture. So we changed V armature. So if we take V armature down from its old value, and its old value was 240 volt, which gives us a speed of 750. If we take this voltage down to 191.52, this will give us a 600 RPM speed. So actually you can construct like a lookup table. Here is the speed, what is V armature for this speed. So if the speed is 600 RPM, we need a voltage of 191.52. We can do this for 650, we can do this for 700, for 750. So we can fill what is called a lookup table. And you can program this lookup table into your microcontroller. And your microcontroller will read what is the input speed, what is the speed that the user will need. And will go into the lookup table and find out what is the voltage which will give us this speed. And the microcontroller will output this voltage to the armature, which will reduce the speed down. But this is called an open loop control. We can call this as an open loop control. And to do this open loop control, you need full understanding of the circuit, which has to be accurate, and your equations has to be accurate. So we did some examples for shunt machine and series machine today, and I will leave one question for you to do as a homework. So please do this question as an homework. Already the solution for this question will be posted in the study package for this chapter. So please do this homework before our next lecture